Good afternoon, students of the course TEQU 4006. And some of you requested that I prepare a video for discussing a little bit more about a mass balance around a CSTR type of equipment, and where we have a reaction, a chemical reaction. In this case, in particular, I have a molecule of A, component A, right, reacting to form a component B. In this case, a reaction. This is an elemental reaction, and what you see is what you write. For example, the rate of reaction for A is a constant K times A. So it's a first order type of reaction for A, for the disappearance of component A. Now, a CSTR has an input, a flow rate getting in, and a flow rate coming out. In order to keep the volume at the same level, flow in and flow out must be the same. And basically, you can have a concentration of A getting in at a given, this is a constant number, mole per liters. And as you can see, there's no B. B is zero. The entrance of B into this reactor is zero, which, I mean, that's for this case, could be any number as well. Since mostly we in this reaction is B is formed, so at the exit we will have B, and whatever A that is not completed reacted, then you will have B as well. I mean, sorry, A as well coming out down here. Okay. So before starting anything, let's talk about a little bit about the kinetics that is happening here. As you know, we define the kinetics. In this case, it's going to be defined in terms of A, and that kinetic basically is equal. Now, the coefficient in front of the component A is 1, so that will be negative 1 over 1 by the change of the concentration of A with respect to time is equal to, now what is the element, I mean the coefficient in front of B? That was a 2, so that's what will be 1 over that coefficient times the change of B with respect to time. Okay, we want to clarify that very quickly so that when we introduce now the mass balance around the CSTR, we take care of those coefficients as part of. But those are related to the kinetics, okay? And that's very important because if this were basically a batch reactor, that would be it. I mean, we can use this to get our mass balance, and that's basically it. But it is not a batch reactor. It is a CSTR. Continuous, meaning that there's an entrance of material, an exit. Steering, because there's agitation. Tank is a tank, and it's a reactor because there's a reaction as shown here. Now, we clarify that. Now we can start work on the general mass balance. Basically, we will do a mass balance. Let's start a mass balance for component A. If we start that, then basically what we have is the flow in. Remember, this flow and this flow are the same. I mean, sometimes you can name this Q1 and this might be Q2, but if we want to have a constant volume, at the end of the day, this flow and this flow must be the same, meaning that I can go here like this, Q. Sorry for this. Another important aspect of this is mostly the density of this flow here and the density of the flow coming out of the reactor are as well. Sometimes they are named like rho 1 and rho 2. Those are the density. But again, those density are mostly the same, meaning that I can certainly, for the general mass balance, since the volume is constant, the change in the overall mass balance will be 0, right? So, and that's another story that you want to be, be sure that that's the case, which is it is the case in most of these reaction in where mostly there's a lot of solvent, which could be water, and few molecule here and there. So that end up being that in overall, the overall mass balance is 0. Or dm, right? If I run here like a dm dt, how the mass in this reactor change, it depends on the flow of mass coming in versus the flow of mass coming out. Since what I'm saying is that Q1 times rho 1 minus Q2 times rho 2, since the density are the same and the flow are the same, this term, the m dt, the overall is 0. That will not change. All right? And that allows me as well to come out with this fact that V is a constant. All right, clarify that. Now I can go back now and do the mass balance for A. For A, that will be Q times whatever A get into the reactor right through here times delta T. You check the unit. This unit here will be moles getting into my reactor minus Q times whatever concentration come out at the exit, A here, times delta T. Now, here's the part. According to this reaction, A is disappearing. So that would be K times A. Remember now, careful here. The unit of RA are mole liter per second, meaning that somehow I need to multiply this by the volume by delta T. Now I have here moles, so here is mole and here is mole as well. So the units are consistent, and that's very important. We have a say in Puerto Rico that we always add oranges with oranges. If you add oranges and banana, then something bad will happen. See? Always have to have the same units. So according to that, since this is in, this is out, this is consumed, that's why the negative is there, then the next thing that I have to do is this equal to how the mass of A, particularly A, not the total mass, the component A change. So that's simple. That would be if I have a volume here, and whatever come out here is the concentration inside my reactor. So if I have a concentration of A coming out through this flow, that means that the reactor is at that concentration. And that happens as well with B. All right, so that would be the mass of A inside the reactor will be simple, the volume of that reactor multiplied by A. Since this is the change, that means this is at T plus delta T minus B times A at a time T, right? How this change, will that provide me the accumulation term that I need for this equation? Let me get this a little bit lower so don't get messed up with anything down here. That would do. So the next part here is basically, let's divide by delta T, both sides. And if you allow me to get this a little bit better, there we go. Looks much better. Now, in the limit that delta T tend to 0, this part, the right-hand side part, will become a differential equation. The delta T cancel out here, so you end up with Q times A in minus Q times A minus KAV equal. Now, this is the differential equation that will be like this: dt over dt times V times A. Now, the nice thing about this expression is that V is a constant, so I can take that V out. If it happened that V is not a constant, this equation will end up looking like this, because you will have to apply a chain rule here. It will look, just for the entertaining the concept, will be like 8 times the derivative of the first plus, in this case, V times the derivative of the second, and we end up like this. Now, the nice thing is that V is a constant, meaning that all these terms disappear, is 0. So equal V dA dt, if I divide it by, well, let's put it this way, so I don't want to confuse people. So I end up having that Q times the concentration at the inlet of for A minus Q A minus K A V. If I divide it by B, the whole expression, I have then my differential equation that is used for that, I generate this through a mass balance for component A. That means Q, let's break some part here, Q over B times the concentration at the inlet minus Q over B times the concentration of the outlet minus K times A. All right. So the next thing that I certainly can do is Q over B for CSTR has a very significant meaning. In fact, I'm going to introduce that right now. It's called, the variable is called tau. It's called residence time. How much time is required to change a total volume of the reactor? That's expressed right here. Tau equal V over Q. V over Q. And the unit typically are like, for example, if V is liter and Q is liter over minute, obviously this will be minutes. Okay, that's a resident time. How much time is required to change a volume of a reactor? If I apply this definition here, we have dA dt equal the concentration in over tau minus, here I can associate these two, so I will have parentheses here, 1 over tau plus K times the concentration of A. And that's it. That's basically the balance that we will have for component A. Now, the only thing that I need is, what's the initial condition? Let's say that at time 0, what is the concentration inside the reactor? Please do not confuse that with A in. This is coming from the outside. At time equals 0, what is the concentration of A? Let's say that is in general term. I can call that A0. And that will do. So here we have the mass balance for component A. How about component B? Now, again, check the reactor. I don't have B here, so B in here is 0. That's all what I'm saying. When you do that, let's work that out. Basically, it's the same as I did before. Let's say that I have, like for example, let's say that I have a flow in Q time B in, right? But we are saying that is 0. Hold your horses. This is a general expression. Time delta T minus QB times delta T. And here is the part that confuses most people. B is generator in the reactor. So that definitely has to be positive because, you are generating through a reaction B. And now that's when this comes handy. Because it's saying that if I know A, which I know that reaction, I know the ADT, the only issue that I have to be considered is what is the VDT. For that particular case, the rate dVdt is equal to, right, dA, I can, let's put it this way, to the ADT, negative. But what is the ADT? I know that. The ADT is, if I put it in terms of this, it's going to be minus minus, and that's going to be a positive 2K times A. See? Because remember, and please do not forget that the ADT negative here is equal RA, but RA is K times A, meaning that the ADT is negative Ka, right? So if I substitute the definition of what is dA dt, dA dt, which come from here is minus Ka, minus minus, that will be positive 2. So in my mass balance for the reaction of B, have to be careful here and have a 2Ka, the same apply, and this is mole per liter per second. You have to multiply by the volume and as well by delta T, and that has to be to the general balance of B. That would be BA, sorry for that. It will be B times B volume at a time T plus delta T minus B times B at a time T. Again, divided by delta T all expressions at the limit when delta T tends to 0. That will provide, and a general expression will be Q B in minus Q B plus 2Ka B equal D over dt, volume times the concentration of B within the reactor. Now, again, volume is a constant. All right, so I can take volume out, and eventually you will end up with an expression that looks pretty much like this: dV dt equal, if you remember, I will apply the definition of tau. So you, well, should I apply it now or apply it later? Well, let's apply later. So you will end up like QV B in minus QV times B minus 2Ka. All right, so the only thing that I need is to apply the definition dV dt equal, now V in over tau minus V over tau minus 2, oops, why is minus here? Sorry for that, guys. Oops, let me fix this. Got carried away. It's being generated, so it's positive, and here is positive, so that will be 2 over K, 2 times K times A. There we go. Now, as I said, the concentration of any material for B in is 0, so this term disappear. So I end up having only this equation: dV dt equal minus B over tau plus 2Ka. Perfect. So let's get the other one nearby. Let's get this one so we can tackle them. Copy. Let's put it here. The only thing that I need is let me put this in order. I like to put, okay. Now the only thing that I need to tackle here is the fact that at T equals 0, what is the concentration of B? Let's put 0. Good enough. Because B is being produced through the reaction. So I have here my 2 differential equation for my CSTR mass balance for a reaction of the type of A. It's an irreversible reaction forming 2B. Now, how we solve this? This is the first part. Pretty much this is what's done on the CSTR for the dynamic part. I'm solving. I just did this mass balance, and when I solve these equations, eventually I will have the dynamic of my 2 components, how A disappear and how B is formed. All right, so let's work this out. For the first equation, I take a look at it. What is the independent variable? Obviously, it's time. Time in essence is not here explicitly, So how about the A? A is the dependent variable of time, and it's here, but it's not here. All right. So meaning that all this function here is a function on the right side, a function of A only. How about the second one? Well, the second one is definitely more complicated because it has B here, which is a dependent, the variable of time, and it also has A, which is also a dependent variable of time. So two variables. This need to be solved together with this one. How about this one? Well, this one, since there's no B around here, this can be solved independently of this one. And that's great. That's very good. That's good news. So let's solve this equation. And to solve that equation, let's do this. Let's say dA dt equal, I don't like so many variables to carry them around. So let's call this alpha minus beta A. That's the life is easy when you do that. Suddenly the equation that was kind of ugly end up being pretty and easy. In fact, I don't know. Maybe it's just my thought. It looks more elegant and easy to visualize what it is. Remember, alpha is a constant. By definition, you know what I'm saying basically is that alpha, just right here, is the concentration at the inlet over tau, and beta is 1 over tau plus k. See? That's it. Let's get this. All right, there we go. Now, how we solve this? There's several techniques that you can use to solve this differential equation of first order, or this first order differential equation. Definitely, the first technique that I will try to apply quickly is variable separation. So can I separate the variables? So in other words, can I have time in one side and concentration of A at the other side? It looks like the answer seems yes, I can do that. Because alpha being a constant, it doesn't matter where the alpha m, because basically it's not a function of time or a function of B. That's good, meaning that I can do this and I end up with this. dA over alpha minus beta A equal dt. So I can integrate both sides as part of my effort of variable separation. At time 0, the concentration of this side, let's say that I start with a concentration A0. And now at a given time, this will end up at a given concentration of A, which I would like to know. So to integrate this, when you take a look to what is the polynomial at the denominator here, you say, that's order 1, this is order 0, so this smell like a logarithm, and it is. I mean, let's use a transformation here. Let's use a definition. U equal alpha minus beta A. So du is equal minus beta dA. So dA basically, oops, this looks ugly. dA equal du over beta negative. So if I substitute this here, that end up being the left-hand side. I will not worry about the limits because I eventually will recover back my original variables. So hold your horses there. Don't despair. Help is on the way. So what is dA? dA is minus du over beta. I can put the beta here. In fact, I can put the negative outside as well. And alpha minus beta A. Oh, that's the definition of U. So it's very straightforward to find out that this is minus 1 over beta, and this is definitely the definition of logarithm of U, which eventually I recover my original variables, that the definition of U is alpha minus beta A, the concentration of the material. Since now I am in my right variable, so let's get the limits, A0 and A. If I do that evaluation, that will be minus 1 over beta I'm missing one thing here. Oops. This is logarithm. Opa. Let me get this, fix this. Minus 1 over beta. There we go. Logarithm of alpha minus beta A. Now, 1 over beta times the logarithm of alpha minus beta A. All right. Now, here, careful here. Minus parenthesis the full function again, that would be negative 1 over beta logarithm of alpha minus beta A0, close here, this with this, and this with this. All right. Now, here, minus minus, that would be a positive. But this is a logarithm, and this is a logarithm. I can apply a rule for logarithm and for subtraction, and that end up being now positive 1 over beta. Now this is going to be positive, meaning this will be the numerator, alpha minus beta A0 over the denominator. That would be alpha minus beta A. Excellent. Now I just completed all this left hand side has been completed. The only thing that I need is this right hand side. That would be like this. dt, the integration of dt is t evaluated between 0 and t. That will be t minus 0, and that will be t. Meaning that all this effort here is equal to t. That's it. Typically, I want to solve for a because a is the variable that is a function of t. So I want to get that out of there. How I do that? Well, how about if I multiply by beta both sides? If I do that, then I end up with logarithm. If you don't want me to see writing too much, how about I copy that, put it somewhere here, and that equal beta t. Now I have this and this. How about if I, again, this is inside a logarithm. To get that out, I have to eliminate the logarithm. If I elevate to the e power, all these, the logarithm will be gone. So this is the nice things about my surface. I can paste that again, and that will be equal e to the beta t. Now, at is down here. How about if I take the reciprocal of this? That would be alpha minus beta at over alpha minus beta A0 equal e to the minus beta t. We are about a baby step to get the answer finally. If I solve for at, everybody will agree that this is basically, I multiply this by this. If I add, well, let's get it right. So let me do it slowly, so no, everybody don't get confused, nobody get confused or left behind. Time e to the minus beta t. Now, this part basically will go this way, will be positive, and this part will go this way. That would mean that it's negative. So at the end, I will have something like this: beta at equal alpha minus beta A0 times e to the minus beta t. If I divide by beta, both sides, I end up having that at finally is alpha beta minus A0 e to the minus beta t, which is kind of very, very interesting, because basically what I'm saying now is that as time goes to infinity, at, if you put infinity here, that e to the minus infinity basically is 0, 0, all this is gone, and you have this. So you have equilibrium. That's basically what I'm saying on this type of problem. You have equilibrium. Like, for example, basically what I'm saying is you start at a given concentration of A0 in your reactor, eventually that reactor, depending of what is the definition of alpha or beta, that reactor will do something maybe like this. So, and that value there is alpha beta. Take my original equation, which was this one, dA dt alpha minus beta A, and when there's equilibrium, the concentration of A will stop changing, meaning that this is go to zero. And now from the same differential equation, you can add, when this is go to zero, you have an algebraic equation here. Now solve for A, meaning this is equal zero, meaning that A is equal alpha beta as well. And this is from the differential equation, not through the analytical solution. This is the analytical solution that you can, you take and you the answer at when t, let's fix this, when t is infinity, that would be alpha over beta. That's good. So now we solve basically here for the concentration of A for one particular method. This is variable separation. I think that we can apply as well the method of integration factor. Let's see how will that do. So let's see how well we can apply integration factor to our differential equation. Let me start by putting a new page here, add page, and that would be something, let's say that my concentration of A with respect to time equal alpha minus beta times the concentration of A. That is for the mass balance of A, component A. How about the mass balance? Let's see. Leave it like that. I would want to. I thought to put the B, but let's see. The concentration of B, in particular, was kind of was like this. Let's put it this way here: dV dt equal minus B over tau plus 2k times A. All right. So obviously, this one. Now that we know what is A, we can start to work with this one as well. But before I do that, let me do integration factor on this one, because this one is all in terms of A, so it should be easy to work that one. First of all, if I want to do integration factor on this equation, let me do a definition, right? A definition, a very general definition that is easy to memorize, is like dy dx plus px times y equal qx. It's a non-homogeneous equation with a value of qx, but the y has something in particular associated, which is a function of the independent variable, okay? Now, meaning that the solution that apply to this equation in general, the general solution is very simple. It's y equal, and that y is a function of x, of the independent variable, which in our case is time. It doesn't matter. Is equal to, now, the integral of qx times a integration factor called ix dx time plus a constant, see, general constant, and all of that divided by ix, which is the integration factor. And that's the general solution when you apply integration factor. So the only thing that you need to do is take a look at your differential equation and let's see how well you can, rewrite whatever is here on this form. So let's do that. This will be like the ADT plus beta A equal alpha. That's it. If you do that, basically what you're saying is that Qx is a constant, it's alpha, no big deal. In fact, instead of calling Qx, let's call it Q of t, because that's the independent variable for my case. How about P? P of t is a constant, is beta. Now, the question is, which I haven't written here, what is the integration factor? But it just happened that the integration factor in general will be E. Oops, I have a problem here with my, there we go. Will be E elevated to the integration of px dx. First, before you applying this expression here, you have to first of all find what is the integration factor that is here. So the first thing you do is try to get this first. Well, obviously, you need to identify what is px, meaning that your function, this function here, has to be written in such a way that looks like this one. So you have to write this like this, and then compare elements. So if you do that, we know now that our I of t is equal to E elevated to the px, but px, and in this case, which is pt, is beta dt. I'm using this. So by definition, meaning that is e to the beta, the integration of dt is t, so that means beta t. And that's my integration factor that I need. So now my solution, which will be a as a function of t, is equal the integration of whatever is qx, which in my case is qt, is alpha, for whatever is ix, but that's beta t. And that dt plus c, and all of that divided by I of t, which in this case is e to the beta t. Now, I'm about a baby step to get this completed, and looks to me the integration factor for this problem will be a lot easier, a very shorter route than variable separation. So at the end here, this is what I'm going to get. You have this integration and you're done. Right. So the alpha is a constant. So let's work on that integration as only. So I have an integration that is e to the beta t dt. That is alpha. Now e to the beta t, beta will come out as here, as for completing the integration, and e to the beta t. And that's it. Now, if I substitute this definition here, which is this part here, meaning that at is nothing else than alpha beta e to the b to the beta t plus c, everything divided by e to the beta t. Now, I need to find the constant. What is c? Well, for that, you only need to apply the initial condition, which was that at time equals 0, A equal A sub 0. So that's the concentration, the initial concentration inside the reactor. Never confuse this with A in. This is the material getting into the reactor, not the material that is already inside the reactor at time equals 0. Never confuse these two, which may happen to have the same value. Oh, maybe. Oh, yeah. You might have that the concentration into the reactor is about 5 moles per liter, just to say a number. And it just happened that the concentration that are getting, that the flow, the material getting into the reactor is about 5 moles per liter, but the concentration inside the reactor is also 5 moles per liter. That could happen. But again, never confuse the two terms. All right, this had nothing to do with that one. A t equal alpha beta. This and this cancel out, plus c times e to the minus beta t. This is negative. Yep. And that will do. Now, the initial condition is at time equals 0, a equal a0. If I substitute this here, I end up having a0 equal alpha beta. At t0, this part is gone, so you end up plus c. Meaning, finally, that c is a0 minus alpha beta. Meaning that at through this technique of integration factor is alpha beta plus c, but c is a0 minus alpha beta e to the minus beta t. That was integration factor. Now, the one that we did before, which was through variable separation, ended up like this. Alpha beta minus alpha beta minus a0 e to the minus beta t. All right. This is the only thing that is different, which is not a big deal. If you multiply by minus 1 here, this will be minus, which is here, and minus times minus, that will be positive, which is here. It's the same equation. So we end up having the same result, but looks to me that it was a lot easier using integration factor than doing variable separation. Again, it's a matter of taste, or it's a matter of what the professor say that you should use. He say use integration factor, then use integration factor. But certainly you can compare your result with variable separation as well. If it's possible, sometimes variable separation will not work. In this particular case, since right here from the top, since alpha, this one here, was a constant, there was no problem that we could use, in fact, we use variable separation. And we also now demonstrate that we can use integration factor as well. Not a big deal. We are now about to get the other part here, which is, what about b? Now that I have this value here, I'm gonna continue with this one, just for the sake of the argument, it's more of the same. I need to get that into my b expression. Now, if you remember, let's see if I have a b here somewhere. Right here. To get that part, now, to get this working, the problem of this differential equation is that it was a function of b and a. And it will not work like that. I have to get what is a. It happened that I know already what is a. I can put that right here. So I have an expression that looks more like now, like dv dt equal minus b over tau plus 2k. Now I have all this here, alpha beta minus alpha beta minus a sub 0, all that minus beta t, this parenthesis with another one here, since I'm multiplying everything by 2k. All right, that will do. The question is, I have only one dependent variable, which is b, and everything else is a function of time. What will be the method to use here? And that's a problem. I see a problem for variable separation, because basically if I simplify this so that looks more easy for you to understand, what I'm saying is you have something like this, dv dt equal something that has a b here in general, plus another thing that has a function of time here. All this, right? Since this is b, the dependent variable, and this is t, the independent variable, can you separate these two? You can't. you cannot use variable separation. No, it will not work. Variable separation will not work here. So what the only thing that you have left is integration factor. Oh, I do have that one. So since I have integration factor, basically I need to accommodate all this that looks more like integration factor. That's super. This is what you have to do. Now you allow me to copy all this. And that's it. Now I can, you can see what is P, which is the one that is used for the integration factor. P of t, basically on this case, is 1 over tau, but Qx, or in this case Q of t, is all of this. And that will do. So what we need to do is apply a very simple integration factor to get our problem done here. All right, now to keep going, let's, before get all messed up with so many variables all together, we can definitely do a couple of things here to make life easier. Let's say, for the sake of the argument, that alpha beta, this alpha beta, I can simplify that to a new variable, and let's call that variable, let's do this, qt equal 2k, let's call this mu, minus, and let's call all these delta time e to the minus beta t. I'm only, trying to simplify a few things here and there to make life easier. Otherwise, too many variables you will get confused with the real part, which is the v, the dependent variable. So dv dt plus b 1 over tau equal, now you can get this straight, that would be 2ku, 2k mu, sorry, minus 2k delta time e to the minus beta t. I'm only making life easier, and don't get all bogged down in definition. Like I said, mu is just alpha over beta, and delta is equal alpha over beta minus a0. See, they are just number, no big deal. Now, the only thing that is important when you do that, again, is that I have simplified what is q of t, and now I only need an integration factor. What is the integration factor? I of t for this problem is nothing else that e elevated to the whatever constant is here, that will be 1 over tau dt, meaning that this integration here, that will be dt is t, so that would be t over tau. That's as simple as it gets. So our solution for b, in a very, very general expression, will be b of t of time equal to the integral of 2k mu, right, which is all this, minus 2k time delta time e to the minus beta t, all of that, time e to the t over tau dt. So we need to integrate all that, and that's the integration factor, plus a constant c, everything divided over the integration factor, by definition e over t over tau. So for the first part, 2k mu e to the t over tau dt. If we integrate only that part to make life easier, we have 2k mu. So we have an integration factor that show up as 1 over tau to complete the integration e to t over tau. So that's the first part for that integration. Now we move to the second part. That will be the integral of 2k delta e to the minus beta t, and that had to be multiplied by et over tau dt. And now you have same base, so you have to add up the exponent there. To simplify that, that would be 2k delta times e to the sum of those two. One is negative, one is positive. That will be 1 over tau positive minus beta and all that time t. All right? And that will be dt. So if we integrate that part there, yeah, let me put the negative here so I keep all this straight. Don't get people confused. So that final part there will be minus 2k times delta e. That's going to be the integration factor, 1 over tau beta. Oops. Let me fix that. Beta. And all that elevated e to the 1 over tau minus beta, parentheses, time t. So I got the two part. There we go. So now you can see both part, how I did it. So now if I put the both together, v of t will be, the first part is going to be 2k mu over 1 over tau e t over tau. Now minus the other part is going to be 2k delta e to the 1 tau minus beta tau t, sorry, all that part divided by 1 over tau minus beta. That's it. Now I have plus c. Now remember that if we apply integration factor, everything has to be divided by the integration factor, that is et over tau. There we go. If we simplify a little bit all this, you can see that the first et to the over tau cannot cancel out, so we get the 2k mu over 1 over tau, and that's it. For the second one, we get, if we take a look, that t over tau is also back there, t over tau, so that cannot disappear as well from that expression. Just subtract those exponent on there. So that would be 2k delta over 1 over tau minus beta, and e to the minus beta t. See, the 1 over tau disappear. Plus c, and that c has to be is over then e t over tau. That will end up being negative at the exponent. So at this point, we only need to look for how to solve for c, which is the constant. Oops. There we go. So to solve for c, we need initial condition at t equals 0, b is equals 0. So we don't have nothing inside the reactor at time equals 0 for b. For a we do, but for b is 0. Again, don't confuse being with b. That's another story. In order to simplify for C, let's call new variables. I hate to write so many variables. Let's call that BT equal, if we simplify these and we call all of that with a new letter, uh, that will make life easier. And so this one will have a letter A. For that, how about this? That would be B times e to the minus beta t plus C e to the minus t over tau. So let's apply the initial condition for B, and that would be a time 0, B 0, so A minus B, B to the 0, that's 1, so you end up with B plus C e to the minus t tau, obviously that's also 1, so we solve for C, C equal B minus A. So our expression is A minus B to the bt beta t plus B minus A e to the minus t over tau. And this expression is the solution for the dynamic of the B concentration. Now for A is alpha beta minus alpha beta minus A0 e to the minus beta t. And this is the second expression for A. So now we have A and B, how that the dynamic of the concentration within the reactor. It's interesting that at T infinity, BT equal A, right? That's it. That's the only thing that survived. Now, if we look for that definition of what it is, we get the A value is 2k mu over 1 over tau. So if we remember what it was mu, notice that 1 over tau is tau, and that mu is alpha beta. Let's look for it anywhere here. There we go. Mu is alpha beta, and what is delta as well is right there. You know, we don't want to get bogged down in the definition. So that would be tau 2k times mu, but that's alpha beta. And that's our value when time goes to infinity, which is kind of different from this one. A is alpha beta. So somehow they have something to do between each other, but obviously beta, or I mean sorry, B, the concentration of B is modified by tau and by 2 and the factor of 2 and 2k. So here we have all those are the definition at time infinity, and these are the dynamics. And so the only thing that we need is just go to Excel and let's get the plot of this. So here we are in Excel, and basically I copy everything that I need to copy, like for example the definition of B of T, which is in terms of A and B, if you remember, and A and B are defined here. In terms of other variables like mu and 1 over tau and 2k and all that. So I don't bother, simplifying all this to the point that I know precisely what A is all about in terms of original variables. I'd rather, have that done through Excel, and that's it. And whatever it's gonna be will be. So like for example, my problem, let's see, let's get a couple of things here from the original design. Let me move back to here, and let's go back here, and from the beginning, let's see, I got that there. So let me copy that copy, and let's see what would that do. Before I do any discussion, these are the definition of all the variables. Let's see if I get, okay, good. That looks good. So let's go back here and let's put that design somewhere here so that I can ref refer to it. There we go. So I have everything that I need. All right. So as you can see, that's my CSTR with the input and output, good agitation. And let's define some of the variables that I need. Like for example, the flow in, that's right here, liter per minute and that unit. And the concentration of the input A for this problem, you can put any value here. Like for example, I settled with 10 mol per liter. How about the initial concentration within the vessel? Right now, is they are equal? I'm gonna put the different just to avoid confusion. Let's say that the initial concentration is 5. As you can see, there is some movement here at the when I do the graph. No problem there. So basically, this whatever I put in yellow here are original variables. So let's label those yellow. So I got concentration in, initial concentration of within the vessel, the rate constant, and Q. How about the volume of the reactor? Those also, it is a value that you can set before anything. So 1, 2, 3, 4. These 5 variables are the key parameters that need to be set so that the others will follow. For example, tau. Tau is, if you remember, let's see if it's defined here. Actually, that's the only one that I don't see it. But tau is, if you check what is B6, is B over Q, 200 minutes. The volume of the reactor is 1,000 and the flow is 5 liters per minute. That would take 200 minutes to change the content of this vessel at least by 1 factor. All right, so it takes 200 minutes. Now, how about alpha? Alpha is already defined here. Is whatever concentration is getting in divided by tau, which is already defined. So alpha is B2, concentration in, divided by B7, which is tau. How about beta? Beta is also defined 1 over tau plus K. So you can see here the 1 over tau, B7, plus B4. And B4 is the K value. So that's beta. How about alpha over beta? Alpha over beta, we know that when time is go to infinity, all this term will go out, and alpha beta is actually the equilibrium of the concentration that you reach when T go to infinity. So, and you can see here the blue being the AT is just going down to a steady state value. Not yet for BT. It's taking a longer to reach that steady state value. Anyway, mu. Well, mu, I said that that's a combination of alpha, beta, which basically it's just the same definition. It's right here. Mu is alpha over beta, and delta. Delta is alpha beta, but alpha beta is the same as mu, right? So it's this value B10, for example, B10 minus B3, and B3 is A0. So perfect. That's delta. What is A and B? A, the definition is 2K mu over 1 over tau. Basically, tau is, so you can see that I have the 2, the B4, but B4 is K. So that's K. Mu is 11 times B7. B7 is this tau up. B7, yep. That's A. How about B? B is 2 times K times delta over parenthesis 1 over tau minus beta, B9. Excellent. So as I was telling you, it's a lot easier to define this like that, so that eventually, you know, you hit enter, and now the only thing that I need just to do the plot is what going to be the delta t for this system. You can use any number, like for example, let's say 0.1. Now that I'm plotting both graph A and BT, I can see, as I tell you before, that the blue, meaning the concentration of A, is getting steady state value of about 100 minutes. Not yet for the concentration of the B value. So I can definitely increase this to 0.5. Now I can see still 300 minutes and not yet have reached the steady state value. How about if I go minute by minute? Let's see. Did it change? Let's see 0.5 again. 1. I see. Hold it for 1 second. Let's put 1 minute here, and I have to. Let me check this. 1 second. I will have to increase this to, let's see, 1000 maybe. Yeah, there we go. Now I can see. Let me pull this from there. Yeah, it's just getting to a steady state value of about 18 mole per liter for B, and that's a weird number, isn't it? We need to check that out, because basically what I'm saying is the initial value A0 start here and then it disappear. So it got to a steady state value of this, whatever is this here, meaning alpha beta, and alpha beta is 0.9, and this is the steady state value. So this is what I'm seeing here. Good. Now, meaning that at a steady state value, if I do a little bit math here, kind of I would say back the envelope type of math, I start originally the amount of material getting in. It doesn't matter the A0 anymore. What it matters is the steady state value that I'm starting with. I'm starting with, I mean, the A in is 10, but the exit end up being 0.909, meaning that the difference between these two values is, those are the moles that eventually react to become B. For every mole of A, I got 2 of B. So this number, which is kind of weird, let's find out if it's true or not. So this is what we need to do. Material in minus material out at a steady state value. If I multiply that times 2, which is basically this here, that should provide me the amount of B. This is B at a steady state value. Let's call BSS. Okay, let me move this a little bit out of the way. There we go. So this is the value of B at a steady state. I know A at steady state, AS is basically beta over alpha, and we know that this right here. So basically a little bit higher than 18, and that's true, and that's what I got. So this number, I mean this curve makes sense. I can change many things here, and let's see what happens. Like for example, let's say the A0 and A in are identical. So let's drop this to 5. Interesting. So now both get to the steady state value very quickly. And as you can see that the value is a little bit higher for B. It's a little bit higher of 9, which is being shown here. Excellent. And the steady state value about 0.45. And that's A in A0 equal. What happens if the concentration inside the reactor is higher than whatever is getting in? Let's see. Let's put A0, let's put 10. Well, that's a weird reaction. So I start here at 10. It dropped quickly within less than 200 minutes. I would say 100. I got to basically the bottom of alpha beta very quickly. Went down. Now the B went through a maximum, and the maximum was close to 16, but then it dropped to a steady state value, which about 9, which is shown here. All right. So in other words, at the end of the game, you know, the initial concentration, it would not matter. This, what it matters is this. because this one will change eventually, whatever you produce at the end. So like for example, if I increase this to 10, then you see it back again, the value of 18. And those are the numbers that I have before. I would say that's basically it. How to get these two equations. I can, you know, put this double click there so you see what is happening. That's A. That's basically alpha beta, but that's B10. That's this one. Minus parenthesis B10 minus B$3. B$3 is A0. Careful when it says A0 is A0. When it says A in is A in. Don't confuse that. All right. Times the exponent of minus beta t, minus 1 times beta t. The time is taken from here through the delta t, whatever you want to start with. Well, that was the A, concentration of A. Let's give enter here. How about this one? This one is a little bit longer. Let's see what we got here. Let's double click on this one. So I have here the letter A. That's $13. Remember the dollars. Anything that need to be a constant, you have to add a dollar. $13 minus $14. That's this B. That's this one here. And times e to the minus beta t. This is beta t plus b minus a. And this term will go away when they are identical, right? So we know that. Times the exponent of minus 1. Now here the formula is minus t over tau, and tau is 7. Be extremely careful. Do not add more parentheses as the one shown here for clarity. You start to add parentheses here and there, or then suddenly it's a mess in order to try to understand what's going on. What I see this, pretty much I'm doing what is shown here. Don't confuse the whole thing by adding more parentheses than is really required. Treat them like they cost you $500, and every time you use a pair of these guys of parentheses, it's because it's required. Otherwise, the equation would not be valid the way it was written. I would say at this point, I think that we have more than enough. This video is already way too long, but the idea was, hey, to show you how to do a general mass balance for component on a CSTR reactor, understand the kinetic, what I will do with this part here, how can this relate to the mass balance of each component, solve each differential equation if possible with variable separation. That's my first try. If not, then settle with perhaps integration factor. If none of those two things can be used, because probably it may be the equation is highly nonlinear, then you can still use Euler and solve the mass balance using the Euler method for first order differential equation. Well, as I always said, that's it. Have a great day. Be careful. COVID-19 is still out there, waiting for people to fall. And I know that you are not those kind of people that will fall into it. So please protect yourself. Have a great day. Bye.